For the invitation to speak here. What I'm going to talk about is more or less a random collection of things that I discovered or learned about or found out about from other people based on Sloane's work on integer sequences for so long. And it's a little bit of a personal history for me because my association began pretty early on compared to the publication of the book. Well, I guess I should turn this on. Now it's good. Okay, so this was my Christmas present in 1974. Do I need to use the microphone, or can everybody hear me? Yeah. This was my Christmas present in 1974. I can't even remember how I had it on my list. Maybe it was mentioned in the Fibonacci Quarterly. Maybe it was mentioned in Martin Gardner's Mathematical Games column. But as soon as I heard about it, I thought, oh, this is obviously the book for me. And I told my parents, and of course they felt this was rather odd. But they were very indulgent. And in 1974, this arrived. And actually, Neil, he never did autograph it for me. So I was very excited by this. To me, it was like a map to many, many undiscovered countries. And you could just open a page, and there would be numbers marching along, mysterious and sometimes symmetric and interesting and intriguing, and coded in this very bizarre code that you had to master by looking at the back of the book to figure out what ER132 meant. And then, of course, back then we didn't have the internet, so once you discovered what ER132 meant, you had to go to a mathematics library, which for me was the University of Pennsylvania. There on the weekends, or sometimes even on the weekdays, I would sit there and happily Xerox the articles and try to read them. And I failed over and over again to understand a lot of what was going on, but still it was so wonderful. Well, you know how J.D. Salinger writes in Catcher in the Rye that when you read a book, you wish the author were this terrific friend of yours so you could just call them up and chat with them? Well, when I got that book, I thought, wouldn't it be great if Neil Sloane were this terrific friend of mine and I could just call him up? So I wrote to him. I think it must have been December 26th. The reason why I think it had to be that is because I got a reply dated December 31st, which I still have. And he said, "Thank you for your very kind words about the book." So I must have said the same kind of thing that you might say to J.D. Salinger. And he gave me the supplement, which I still have. He didn't autograph that. And see, what I wrote him about was I said, I really loved your book, but how come it didn't have the continued fraction for E in it? And he said, because it's very dull. And I thought, oh. But then he said in response to public demand, it will go into the next supplement, which I don't think ever existed. Oh, there was a second supplement? Oh, okay. Anyway, so not only did he write back like within 3 or 4 days, but he was kind and happy to talk to me, which is very unusual, I think, to speak to some random 17-year-old writing you about the continued fraction for E. So thank you so much. And he continued. I won't show you all the other letters. We continued to correspond for a while, and I was contributing sequences and correcting some errors, and I wrote some multi-precision code, and it was just a huge adventure to me to be part of this labyrinth of mathematical worlds and explore them a little bit with somebody who is an expert. So it was a real thrill for me as a young person. Anyway, so what I want to do is just tell you about some of the weird sequences that I came across, and I'll mention a few open problems, and maybe some people will be sufficiently motivated to think about those open problems. Some of them have been open for a really long time, and it would be nice to know about them. So I'll start with this modified Engel expansion. So Calpizito, Knopfmacher, and Knopfmacher in 1990 paper, they studied expansions that looked like this. So in case you just don't see the general term, it starts out with an integer, and then plus 1 over a1, and then a1 plus 1 times a2, and then a1 plus 1 times a2 plus 1 times a3, and so forth. And these ai are non-negative integers. And this expansion is more or less unique with some conditions about the stopping that you have to enforce, provided that numbers are strictly increasing. So when you try expanding some numbers, well, here's what happens when you try expanding 2 over 5. So when you do that, you get the following sequence: 2, 3, 7, 13, 97, 193, and so forth. Now, first thing you notice is it looks like it's doubly exponentially growing. And one of my favorite papers as a 16-year-old was a paper entitled Some Doubly Exponential Sequences, which I would sit in front of the TV on Sunday night and watch Walt Disney while trying to understand this paper. And it was a little bit rough going for me at the time, but I got something of the gestalt behind it, and it just seemed so beautiful. And so when I saw that, I thought, oh, it's got to be one of Sloane's doubly exponential sequences. And in fact, if you look at the even index terms, in fact, you do get one of these. And it turns out then that this expansion for 2/5 looks like, can be given like this. So the odd number terms are this to the I, and the even number terms are very closely related. So that was something that I found immediately just by looking up. And then more generally, you can get the expansion for 2 over 2r plus 1, and it looks very similar. But there's many rational numbers for which we still have no idea what their expansion is. By that I mean some relatively simple rule giving the expansion. Obviously, the expansion itself gives a computable interpretation of the sequence, but something similar where you can say something about the growth rate. For example, is it doubly exponential? Is it just exponential? Whatever. And for 3/7 is the smallest numerator and denominator for which I have no idea what the expansion is. How quickly does it grow, for example? So that's something you can easily program up in a language that has extended precision arithmetic like Maple or Mathematica, and you can look at thousands of these and try to find interesting patterns. So it's kind of fun. Okay, here's another one. This is a sequence where you start off with 2 initial values, and then Cn is defined so that basically the quotients of adjacent terms are going to be strictly increasing, but as slowly as possible. Right? So the quotient Cn over Cn minus 1 should be greater than Cn minus 1 over Cn minus 2, and it should be the smallest possible one. So now, for many initial values, this is very easy to describe. For example, if a is 1 and b is 2, then we just get the 2n plus 1 Fibonacci number. And if a is 2 and b is 3, then Cn is 2n plus 2 to the n plus 1. And so I think a natural conjecture is that whatever 2 starting values, this is going to satisfy some linear recurrence. But that's not true. So for example, for a is 8 and b is 55, this is the resulting sequence you get. And if you just try to guess the linear recurrence, I try to tell my students that if you have some sequence and you don't know what it is, very first thing you could try is see whether it seems to satisfy some linear recurrence, which after all, just solving some system of equations. But this seems very foreign to them to treat mathematics as an experimental science. I tried to get across to them that this is something you can do. So, of course, you can try to guess a linear recurrence. And when you do that, you get this linear recurrence, which the sequence seems to satisfy. And indeed, it satisfies it for the first 11,055 terms. But at the 11,056th term, it no longer agrees, which cries out for some kind of explanation. And this explanation was found by David Boyd. And the basic idea is that if you look at the roots of the characteristic polynomial, then there's one real root, which is about 6.8. There's another, which is about 0.9548. And then there are 2 complex roots. But look, that the magnitude is almost exactly the same as the second real root. And so there's a certain cancellation effect that goes on in this. And it works really well for a while, but after about 11,000 terms, then suddenly the errors accumulate, and this sequence no longer matches. So Yeah, so the quotient is very small, a smaller real root with the magnitude of the imaginary root. So that's the deep reason behind it. And in Boyd's paper, he still doesn't have a complete classification for which starting values there are linear recurrences. And that sequence 10918. Yeah, so it's still not known exactly which of these satisfy linear recurrences. Okay, here's a question. Now, unfortunately, I just got here last night, and I had to miss Richard Stanley's talk. So I don't know if he talked about this or not. But if not, then I'll just mention it. So this is something I found as an undergraduate, which is how many distinct monomials are there if you multiply out these indeterminates as a polynomial? So for 1, you just get 1 monomial. And for 2, you just get 2 monomials. And for 3, now you get 5, right? Because you can get 1, 2, 1 in 2 different ways. And for 4, you get 14, and probably now you can all guess, especially with a hint, that these are the Catalan numbers. So as an undergraduate, I noticed it, and it took me quite a while to prove it, and it later appeared as a problem in the monthly. But, so first I typed these in, I looked in Sloane, and oh yeah, of course it must be the Catalan numbers, but it took me a while to prove it. So that's another Catalan appearance in the world. Okay, I'll talk a little bit about a subject that Eric has been working on, which is lexicographically least sequences, avoiding patterns. So what I have in mind is, for example, you might want to avoid squares. So by a square, I mean 2 consecutive blocks in a sequence that are exactly the same. So in English, the longest example I know is the word hotshots. H-O-T-S, H-O-T-S. So it's a square. 2 consecutive blocks that are the same. And now what I want to do is I want to try to make a sequence, an infinite sequence, that will avoid squares, but I'm going to do it in a greedy way, starting with 0. And by greedy, I mean I'm always going to pick the smallest number that I can that fulfills the criteria. So we first write down 0, and now you can't follow it with 0 because that would give the square 0, 0. So you have to write down 1, and then you write down 0, which is okay, and now you can't write down either 0 or 1 because both would make a square, so you write down 2, and you keep going. And what you get, and it's pretty easy to prove, is that this is the so-called ruler function, the 2-adic valuation of n for n greater than or equal to 1. So this is the lexicographically least integer sequence over the natural numbers that avoids squares. Well, now you could play the same game with other patterns besides squares. For example, you could try to avoid overlaps. Now, what's an overlap? An overlap is a pattern of the form AX, where A is a single letter and X is a possibly empty word. So if you think of AX followed by AX, that's a square, and then one more letter. So an overlap is like just slightly more than a square. An example in English is the word alfalfa. A-L-F, A-L-F-A. In French, entente. Another example. So we can try to avoid overlaps. Now when we do this, here are the first, 75 terms or so. So let's see what happens is 0, then 0 is okay, because that's not an overlap. Then the next one can't be 0, because that would be an overlap, so you have to put down 1, and so forth. And you keep doing this, and now here, at this point, you're stuck with 0, you're stuck with 1, so you have to write down 2, and 3 doesn't appear here. This question is, what the heck is this sequence? What is it? What's the rule? It doesn't seem to be as easy to describe as the example based on the 2-adic valuation. So what is it? Well, a student at Waterloo and I looked into this, Matthew Gay-Paquet, and we proved a number of properties of the sequence. So here's one, which is the first occurrence of I in this sequence is at position 1, 3, 13, 79 for I equals 0, 1, 2, 3. And here is with the position. It's 2 to the n times n factorial times the square root of e. Now, I don't think you would have suspected that e would come into this. What does e have to do with overlaps? And so here's a case where we looked at the sequence. I said, oh, that looks really familiar. I bet that's in Sloane. And I typed it in, and indeed, once we had the formula, then we sort of knew what exactly we were trying to prove, and it became much easier to do. And similarly, the sequence can be generated by iterating the map where 0 goes to 0, 0, 1, 1 goes to 1, 0, 0, 1, 0, 0, 2, 2 goes to this thing. So, what are those? Well, the length of these, again, is just a sequence which is related to the previous one by 2pi plus 1. So you can actually explicitly write down what these things are. And so we understand that completely. But I should say that Eric Rowland and Lara Pudwell are investigating these for other rationals and have lots of results, as I learned this morning. But one that's still open is apparently 5/2. If you want to avoid anything that's a 5/2 power, by that I mean a block followed by the same block followed by at least half the block again, then it seems to be that the lexicographic to these sequence is over a finite alphabet. And indeed, we generated something like 1 million terms. And this is the case, but we had no proof. So that's another open problem. Okay, counting abelian squares. So here's another thing that came up. I was working with Bruce Richmond. So what's an abelian square? It's kind of like a square, except now we consider it in a more general sense. So it's where the first half is a permutation of the second. And I like this. The example reappeared because the first half reappears in the second half. So now you could try to count the number of such things, and there's a very simple proof of this. So suppose you have suppose you're doing it over alphabet 1 through k. Suppose there are I1s in the first half, so you choose the position of these 1s in the first half and the second half, and that can be done in n choose I squared ways. And now the remaining position, you have to fill in the k minus 1 symbols, and that's going to be abelian square. When you throw away the 1s, you're going to have an abelian square on the remaining letters, and therefore you get a formula for ak of n, and it's just this. Okay? And for a one-letter alphabet, well, there's only one abelian square of each length over of length 2n, over alphabet of size 1. And so for A2, we immediately get this formula. And now I can prove this famous identity just using abelian squares, which is a proof I never saw before. So you take a string of length 2n, you choose n positions in it, and if it falls in the first half, you make the item in that position a 1. Otherwise, if it falls in the second half, you make it a 2. And of the remaining ones, you do it the other way. You make it 2 if it falls in the first half, and 1 if it falls in the last half. And that's going to be a bijection between this 2n choose n and the abelian squares, and now the abelian squares are counted by that, as we already saw, so that proves that famous identity. Here's a project that I got involved with Jean-Paul Alouche in the 90s, and this is a class of sequences which are typically relatively easy to recognize. Once you recognize them, you can come up with various kinds of closed forms and know something about their asymptotic behavior. So in that sense, it's a little bit like linear recurrences or something like that. So the idea is you start with a sequence and you break it up into its odd and even index subsequences. And then you do that again with those sequences, and now you're looking at these. And then you do it again, and you just do this forever. And the set of all such sequences, I'm going to call the 2 decimation of the sequence, and in general, k decimation. Okay, well, if the k decimation is finitely generated, by that I mean there's some finite set of sequences such that this dk, this decimation, is a subset of the z span of these finite set, then S is called k regular. And there are many examples in the OEIS and in other places of sequences of this form. So here's a very common example. Count the number of comparisons in merge sort. it's given by a recurrence of this form, and this turns out to be too regular. And here is showing the subsequences as linear combinations of smaller indexed pieces. So that suffices to show that this is too regular. And once you have that, then you can, for example, compute the nth term in polynomial time, and things like this. It also turns out that there's a closed form. So typically sequences that are like too regular will look something like this. That is, it'll be some relatively simple function often of something having to do with the base 2 representation of the number n. So here, floor of log 2n is basically the number of bits in the number. So you can see it has something to do with the base 2 representation. A few more examples. The famous sequence of Mallow's, the unique monotone sequence such that a of n is 2n. The proc sequence, the unique monotone sequence such that a of n is 3n. That's 3 regular. We showed that the lexicographically least monotone solution to a of n is dn is d regular. This part of the sentence missing there. And Ksenia proved in a really amazing paper that the number of binary overlap free words of length n is also 2 regular, which gives a pretty detailed formula for the number of such things. Now here's an open problem related to this. So suppose we define R of n to be the sum of 2I choose I for I between 0 and n. And now I look at the three-adic valuation of this. So this is f of n. Here are the first few values of f of n. So the exponent of the highest power of 3 dividing Rn plus 1. Okay, now if you run, it's easy to write a program which tries to determine if something is k-regular. You just run it through and it tries to, it assumes that if identities hold for, let's say, the first 100 or 1,000 terms, they hold forever. And you can then deduce relations like this, at least guess them. So when you do that, you get relations like this. And from this, you can get that the three-adic valuation of R of n is equal to the three-adic valuation of n squared times 2n choose n, which is not that easy to prove. Now, Don Zagier found an amazing proof using amazing to me anyway, using three-adic analysis for this. And he showed that if you take the quotient of these two things, then three-adically, this is a function from z3 to minus 1 plus 3z3, and it has an evaluation at the negative integers. The sequence was originally due to Nicholas Strauss. I should have said that. Now, here's the open problem. You can look at similar kinds of binomial coefficients, like this sum here. A of n is n choose k times n plus k choose k, summed between 0 and n, and you let d of n be the three-adic valuation. Then, when you run this through a 3 regular sequence recognizer, it produces these relations, at least conjecturally, which hold for like the first 10,000 terms. But as far as I know, nobody knows how to prove that. So that's an open problem. Just to try to prove these relations. So it turns out that a lot of these sequences in the OEIS are k-regular, and they're usually pretty easy to recognize. When Alush and I were first looking at this in the 90s, Neil was kind enough to send us an electronic version of the database for us to play with. And we ran it through our recognizer, and we found about 6% of the sequences at the time were either k-regular or probably. They were probably in the sense that we couldn't prove it. But, so that's a fairly substantial number. I don't know if that probably doesn't hold up for 250,000 sequences. But if it does, that would say, what, something like 15,000 of them are k-regular for some small k. And so I think it would be nice to add a facility to like something like SuperSeeker or something in the OEIS that would check to see whether it looks like it's k-regular. So I think it's a useful class to study. Okay, now the OEIS it just turned out to be useful in so many different ways. Here is yet another place. So this is the rhythmic infinity series of Per Nergard. How many people know who Per Nergard is? and 2. Per Nørgaard is probably the most famous living Danish composer. And he is still alive, and he bases a lot of his compositions on some sort of automatic or mathematical description. And here's one of the ways he generated rhythms. He would start with 2 Fibonacci numbers. He would then replace them with the sum of the 2 previous and switch the order depending on the parity. So for example, we write down 55 and 89, and 55 is 21 plus 34, and now this is in an even position, so that's 55 plus 34. And we just do this all the way down, and we get these, and then he would build rhythms out of this very last line. And now the question is, what is this sequence that results? Well, if you just write out the indices instead of the Fibonacci numbers, and you subtract 4, then you look that up in the OEIS, which is what I did, of course, and immediately see this is just the number of ones in the gray code for n. So that's probably the only composer I know of who writes pieces based on gray code. Okay, here's another thing. This is something I've been doing recently. You know, Hilbert's dream was to have some sort of mechanical procedure that would prove theorems. And of course we know now that we can't do that, but there's still some classes of things where we can write down decision procedures. And most of them are not so interesting, like Pressburger arithmetic by itself. You can't really write down too many interesting theorems that you would like to prove in just Pressburger arithmetic. But if you augment Pressburger arithmetic with just a little bit more, then you suddenly get a fairly large class of theorems that have some interest that people actually want to know. And then it turns out you can prove them purely mechanically. So lately what I've been doing is playing around with a prover written by my student Hamoun Mousavi. And we proved lots of cool results, lots of results that were already in the literature. We reproved purely mechanically, and we found many new results that nobody knew before. So just to mention a few things. The finite Fibonacci words, you probably know what they are. One definition is x0 is 0, x1 is 1, and xn is the concatenation of xn minus 1 with xn minus 2. So we get a bunch of words that looks like that. And Frankel and Simpson, what they did was they counted the number of occurrences of squares in the nth Fibonacci word. By occurrences, I mean you count the square. If it has 2 different occurrences within the word, you count it twice, or 3, or 4. You count with multiplicity. And they came up with the following formula. R of n is this function of Fibonacci numbers. Now actually, their paper had an error. They forgot the 4 there. And I just added that just a couple of days ago. Even though their paper came out in '99, nobody bothered to put it in yet. So please, when you see sequences in the literature, put them in.
Yes.
The question is, you know, is this the kind of thing that you could do in some purely mechanical fashion? And the answer is, believe it or not, yes. So we have software that will take a predicate written in some logical language that asserts that there is a square beginning at position I of the nth Fibonacci word, and then it will count them and it will produce this formula. Okay? So let me just give you a sketch of how that works. So what we do is we start with an infinite word, which is generated by iterating a morphism. So here, 0 gets replaced by 0, 1, 1 gets replaced by 0. If you start with the word 0, it gets replaced by 0, 1, and you apply these rules again. 0 gets replaced by 0, 1, 1 gets replaced by 0, so you get 0, 1, 0, and so forth. And what you get are the finite Fibonacci words. That's step 1. Step 2 is to associate a numeration system with the word. In this case, if you play around with Fibonacci numbers, you know about this numeration system already. It's called the Zeckendorf, or Fibonacci numeration system, where you write every positive integer uniquely as the sum of non-consecutive Fibonacci numbers. So now you have for each n a unique representation. Okay, now the third step is you need finite automata. These are simple models of a computer. The only thing they can do is read an input and based on the current state and the input move to a new state. And they can also make outputs. So we need finite automata. One will read a number written in this Zeckendorf representation and output the nth letter of the Fibonacci word, and the other that adds two Fibonacci representations. If I give you n in base Fibonacci and m in base Fibonacci, it will produce n plus m. Now once you have those, not too hard to construct, you can make a decision procedure that will take any first order query about the sequence using operations like plus and less than